On the 11th day of June 2026, NOAA's Climate Prediction Center upgraded its alert status for the tropical Pacific from a watch to an advisory. The language was careful, as it always is when the agency's scientists are choosing their words against a backdrop of genuine uncertainty. But the sentence at the top of that advisory was unambiguous. El Niño conditions are present in the equatorial Pacific Ocean and are expected to strengthen into the Northern Hemisphere winter of 2026 and 2027. In the Niño 3.4 monitoring zone, the 5-degree-wide band of ocean straddling the equator between 170 and 120 degrees west longitude, sea surface temperatures had crossed 0.5 degrees Celsius above the long-term average. That is the formal entry threshold, the line NOAA draws between ENSO neutral conditions and a declared El Niño event. The latest weekly reading from the IRI at Columbia University, centered on June 17th, had already pushed to plus 1.7 degrees Celsius. The event is not just beginning, it is accelerating. And here is where this debrief gets interesting. As of early July 2026, the ECMWF's seasonal ensemble is projecting sea surface temperature anomalies reaching plus 3.0 degrees Celsius in the Niño 3.4 region by late autumn. The IRI's 24 model ensemble gives a 13 out of 24 agreement for a very strong event during the September-October-November window, meaning anomalies at or above 2.0 degrees Celsius. NOAA's Climate Prediction Center places the probability of a very strong El Niño, their highest official category, at 63% for the November-January 2026-27 season. The single most likely outcome, CPC's own language, is a super El Niño. The last time we saw that phrase seriously attached to a developing event, the year was 2015. And before that, 1997. Tonight's central question is not whether El Niño is here. It is. The question is whether the event now building beneath the surface of the tropical Pacific has the structural ingredients to exceed anything the modern observational record has captured. That is not a certainty. It may not even be the likeliest individual outcome. But the probability is high enough, and the global consequences serious enough, that walking through what the data actually shows is worth your time. I'm not going to tell you that a climate apocalypse has begun. What I'm going to do is show you the machinery, explain the one thing that makes this event scientifically anomalous, and be honest about what even the best models cannot predict from here. Before we go any further, if you enjoy what we do on the channel, hit like and subscribe so you don't miss any of our nightly debriefs. Also, drop a comment and tell me where you're watching from. Let's get into it. Part 1. The event in sequence. To understand why the June 11th advisory landed with such weight inside the climate science community, you need to understand how strange the preceding 90 days were. In mid-March 2026, the Niño 3.4 index was sitting at negative 0.5 degrees Celsius. That is technically La Niña territory, the cold phase of the El Niño southern oscillation cycle, where upwelling of deep cold water along the eastern equatorial Pacific keeps surface temperatures below average and tends to suppress global temperatures. The global weather machine had been running in La Niña mode since late 2024. Spring 2026 was, by the numbers, a cold side of neutral moment in the Pacific. By early June 2026, the same index read plus 1.7 degrees Celsius. That is a swing of 2.2 degrees Celsius in fewer than 12 weeks. To put that in thermodynamic terms, the surface layer of a body of water covering roughly 15 million square kilometers shifted its mean temperature by more than 2 degrees, not through external heating from above, but through a reorganization of the ocean's internal heat structure. NOAA's own monitoring notes that early June 2026 values in the Niño 3.4 region were at record warm levels for that time of year in at least the past 44 years of continuous satellite-era data. Ocean temperatures in the El Niño monitoring region for the first week of June had no historical precedent in the instrument record going back to 1982. The atmospheric response came alongside the oceanic one. The Southern Oscillation Index, the pressure difference measurement between Darwin, Australia and Tahiti that serves as the atmosphere's side of the ENSO accounting fell to negative 14.5 in May 2026. By late June, the 30-day average had pushed to negative 21.9. Strongly negative SOI values tell meteorologists that the Walker circulation, the massive east-west loop of rising and sinking air that sits above the equatorial Pacific, is weakening. When the Walker circulation weakens, it is both a response to and a driver of surface warming. The ocean and atmosphere have locked into a mutually reinforcing feedback. That coupling, as we'll get into in a moment, is the real diagnostic metric, and it is now fully engaged. One more piece of the June 11 picture. The Niño 1+2 region, the narrow strip of ocean along the South American coast, and the first area to warm during an Eastern Pacific-type El Niño event, registered plus 2.1 degrees Celsius by early June. That is deep into very strong territory, and it matters because the great El Niños of 1982-83 and 1997-98 were characterized by extreme warming precisely in this eastern zone. The location of maximum warming shapes which parts of the world feel the event most forcefully. We'll return to that geography in Part 2. Part 2. The hidden structure. El Niño is not a storm. It is not a hurricane or an earthquake, a single violent event localized in space and time. It is better understood as a state change in a planetary machine. The machine is the El Niño Southern Oscillation, ENSO for short, a coupled ocean-atmosphere system that cycles between warm and cold phases on an irregular schedule of roughly 2 to 7 years. The Pacific Ocean is the largest single body of water on Earth's surface, covering roughly 165 million square kilometers, more than the total land area of every continent combined. The equatorial Pacific is the engine room of that ocean, where the sun's energy input is highest and where the coupling between the ocean surface and the overlying atmosphere is most direct. In normal conditions, the trade winds blow from east to west along the equator, driven by the pressure difference between the cool, high-pressure air over the eastern Pacific and the warm, low-pressure air over the Indo-Pacific warm pool near Indonesia. Those winds drag the warm surface water westward, piling it up in the western Pacific to depths of up to 150 meters, and exposing cold, nutrient-rich water along the coast of South America through a process called upwelling. The thermocline, the boundary layer between warm surface water and the cold, deep ocean, tilts downward toward the west like a ramp. The western Pacific is warm and wet. The eastern Pacific is cool and dry, normal. El Niño is what happens when that ramp flattens. When the trade winds relax, the piled-up warm water in the west begins to slosh back eastward. The mechanism that carries it is the oceanic Kelvin wave, a gravity-driven disturbance that travels along the equator at speeds of roughly 2 to 3 meters per second, or about 200 to 300 kilometers per day, always hugging the equator because of the Coriolis effect. The wave is not visible at the surface. It runs at depths of 50 to 250 meters below the surface, a tongue of anomalously warm water pushing eastward through the thermocline like a fist pressing through a membrane. When it reaches the eastern boundary of the Pacific near South America, it upwells, raising sea surface temperatures and pushing the thermocline downward. The subsurface Kelvin wave now running through the equatorial Pacific has been measured by the TAO Triton buoy array and by Argo floats at anomalies approaching plus 8 degrees Celsius below 100 meters depth. That is an extraordinary subsurface heat reserve. It is the heat that is not yet on the surface, and it is still moving east. Severe Weather Europe's analysis noted in late May that the western tropical Pacific was running warmer than it had at the comparable stage of either the 1997-98 or 2015-16 super events, meaning the subsurface warm reservoir is not yet exhausted. More heat is still in transit. What drives these Kelvin waves in the first place is the westerly wind burst, a temporary reversal of the normal trade winds, where the usual east-to-west flow is replaced by west-to-east winds along the equator. These bursts can last from days to weeks. They can be triggered by the Madden-Julian oscillation, a large-scale pulse of atmospheric convection that moves eastward around the tropics on a 30 to 60-day cycle. When a burst occurs, it pushes surface warm water eastward and also generates a downwelling Kelvin wave below. In April 2026, a triplet cyclone event developed in the Pacific, with two tropical cyclones in the southern hemisphere, Mila and Vaianu, and super typhoon Sinlaku in the north, all near simultaneously triggering a major westerly wind burst. These triplet events are rare. The 1997 event had a similar precursor. Part 3. The Mechanism and the Mystery. Here is the question that separates the 2026-27 El Niño from the normal discussion of ENSO events. It is not whether a strong El Niño is occurring. That is now confirmed. The mystery is whether the event has crossed a threshold that would place it in a genuinely new category. And more specifically, what the role of anthropogenic ocean warming plays in amplifying the event's behavior. To understand the threshold question, you need the historical ladder. The three strongest El Niños in the observational record, generally agreed by NOAA and ECMWF, are 1982, 83, 1997, 98, and 2015-16. Each was, at the time it occurred, described as a once-in-a-century event. The Niño 3.4 anomaly for 2015-16 peaked at approximately plus 3.0 degrees Celsius in November 2015, which set a record in the Central Pacific Index going back to 1860, as confirmed by the ECMWF's post-event analysis. The 1997-98 event, while not quite matching 2015-16 in the Niño 3.4 region, produced higher anomalies in the far eastern Niño 1+2 zone. The 1982-83 event was, for years, considered the benchmark, until satellite data began filling in the picture. What the ECMWF ensemble is projecting for late 2026 is a Niño 3.4 anomaly reaching plus 3.0 degrees Celsius. That would tie the 2015-16 record. Some ensemble members go higher. The ECMWF's June 1st seasonal forecast showed multiple members pushing toward plus 3.5 degrees Celsius by autumn. If those members prove correct, there is no prior event in the satellite era to compare it against. The genuine scientific uncertainty is this: does a warming baseline ocean make each successive strong El Niño warmer in absolute terms, or in anomaly terms, or both? A December 2025 study found that super El Niño events can drive sudden climate regime shifts in both temperatures and precipitation, and that this effect could be increasing in a warming world. The mechanism proposed is that a higher baseline sea surface temperature in the Pacific warm pool means that when El Niño conditions develop, the absolute temperature of the warm water reaching the eastern Pacific is higher, which in turn drives more atmospheric convection per unit of SST anomaly. Michel Leroux, a physical scientist at NOAA's Climate Prediction Center, said in May 2026 that while the probability of a strong to very strong event is now 2 in 3, there remains a 1 in 3 chance of an event weaker than that. That honest asymmetry is worth holding. Models have been wrong before. The 2014 event was forecast as a potential super El Niño, with the same kind of Kelvin wave buildup and westerly wind burst activity, and the large-scale ocean-atmosphere coupling failed to materialize. The system stalled. 2015 did not stall. The difference was strong coupling in summer. We are now approaching that same diagnostic window. Part 4. The Historical Echo. The 1997-98 El Niño is the useful reference event, not because 2026 will replicate it, but because it remains the most thoroughly documented super El Niño with a global impact record. In 1997, the warming in the equatorial Pacific began showing up in the TAO buoy data in spring. The Niño 3.4 index reached plus 2.8 degrees Celsius by late 1997. Global weather patterns that winter were substantially reorganized. The southern tier of the United States saw catastrophic flooding, particularly California, where a series of Pineapple Express atmospheric rivers caused billion-dollar flood losses across the state. The northern tier ran anomalously warm. The eastern Pacific hurricane season was exceptionally active. The Atlantic season was suppressed by enhanced upper-level wind shear. Indonesia and Australia experienced severe drought and fires. Eastern Africa received excess rainfall. Peru saw the strongest coastal rainfall in its recorded history, with some stations recording annual totals in a matter of weeks. The event contributed to an estimated 2,100 deaths directly attributed to weather and an economic toll that NOAA placed in excess of $33 billion globally by spring 1998. The 1982-83 event is the older benchmark. It also produced extreme weather reorganization across the globe, severe drought in Australia, catastrophic floods along the western coast of South America, and anomalous weather in Europe. At the time, it was called the storm of the century in climate terms. It was only surpassed in 1997. The difference between 1997 and 2026 is that the baseline ocean temperatures are higher now by approximately 0.5 to 0.8 degrees Celsius globally, relative to the 1981 to 2010 climatological average used in many comparisons. When a super El Niño sits on top of a warmer ocean, the absolute temperatures reached in the eastern Pacific are not merely statistically extreme relative to averages. They may cross ecological tipping points for coral bleaching, for fish migration, and for atmospheric convective thresholds that have never been crossed before. What the 1997 event tells us about the impacts of a potentially stronger 2026-27 event is useful but incomplete. The ocean is a different place now than it was then. The April 2026 triplet cyclone pattern had a 1997 analog as well. In early 1997, a series of westerly wind bursts in the western Pacific, some associated with tropical cyclone activity, delivered the initial Kelvin wave impulse that kicked off the strongest event of the 20th century. The 2026 triplet event involving Maila, Vayanu, and super typhoon Sinlaku may have played a comparable role, providing the atmospheric push that sealed the transition from La Niña conditions to a developing super El Niño in fewer than 90 days. Part 5. What this is not. I want to spend a few minutes here because strong climate events reliably attract a particular kind of noise. The first claim you will encounter is that this El Niño is caused by underwater volcanic activity, specifically the 2022 Hunga Tonga eruption, which injected an estimated 150 million metric tons of water vapor into the stratosphere. The Hunga Tonga event was genuinely unprecedented in the modern record and was studied extensively by teams at NOAA's Chemical Sciences Laboratory and by NASA. Researchers found that the stratospheric water vapor injection may have contributed modestly to global surface temperatures in 2023 and 2024, on the order of 0.1 to 0.15 degrees Celsius. It did not cause and cannot cause a super El Niño. El Niño is driven by coupled ocean-atmosphere dynamics in the tropical Pacific troposphere, not by stratospheric water content. The two systems are physically separated and interact only marginally through radiation effects. The Kelvin waves now propagating eastward below the Pacific surface were generated by westerly wind bursts, not by a volcanic eruption from 4 years ago. The second claim, that this is all manufactured by geoengineering or weather modification programs. No nation operates a geoengineering program of a scale that could alter sea surface temperatures across 15 million square kilometers of ocean. The energy budget required to shift the mean temperature of the equatorial Pacific surface layer by 2 degrees Celsius is on the order of 10 to the 22nd joules. The total annual electricity generation of the entire human civilization is approximately 10 to the 20th joules. The math does not permit geoengineering of this scale. What is altering the baseline conditions of the Pacific and altering the amplitude of each successive ENSO event is the cumulative forcing from greenhouse gas emissions, which is well understood physics operating continuously over decades, not a secret program. The third claim is that the transition from La Niña to Super El Niño in fewer than 90 days is unnatural and therefore suspicious. It is unusual, yes. It is also physically explicable. The subsurface heat content in the Western Pacific warm pool had been building for months. When the westerly wind bursts of spring 2026 triggered the Kelvin wave, the system had an exceptional reservoir to draw from. Fast transitions have occurred before. The 1972-73 El Niño transition was similarly rapid. Rapid transitions tend to produce stronger events because the coupling engages while the ocean heat content is still near maximum. This is not a fingerprint of manipulation. It is a known feature of strong ENSO development, described in the peer-reviewed literature for decades. Part 6. The 3 readings. So where does that leave us tonight, in the first week of July 2026, with El Niño officially declared, with a Kelvin wave running at +8 degrees Celsius anomaly in the subsurface, and with ECMWF projecting +3.0 degrees Celsius at the surface peak? Reading 1. The strong but manageable event. This is the most defensible current position, and it is where the probability mass of the IRI ensemble sits. Most ensemble members produce a strong to very strong El Niño, peaking in the Niño 3.4 region near +2.0 to 2.5 degrees Celsius by late 2026. On those numbers, the 2026-27 event would rival 2015-16 and 1997-98, but would not clearly exceed them. The global weather reorganization would be significant. A suppressed Atlantic hurricane season, an active Eastern Pacific season, elevated flood risk in the southwestern United States and Peru, drought risk in Indonesia and northeastern Australia, and a global temperature signal of 0.1 to 0.2 degrees Celsius atop an already warm baseline. Serious impacts, well within the historical range, not a record-breaking event in ENSO terms alone. Reading 2. The record-breaking super event. This is the reading that accounts for the upper tail of the ECMWF ensemble and the specific anomaly of the current subsurface heat reservoir. If the Western Pacific warm pool continues feeding anomalous heat into the Kelvin wave over the next 2 to 3 months, if another series of westerly wind bursts arrives in July and August, as the current seasonal forecasts suggest, and if the ocean-atmosphere coupling remains as strong as it now appears, the event could peak above +3.0 degrees Celsius and set a new record in the Niño 3.4 index. On those numbers, the global impacts would scale accordingly. Coral bleaching events across the tropics would likely be severe, as absolute ocean temperatures in the Indo-Pacific exceed the thermal thresholds for mass bleaching. The fire seasons in Australia and Indonesia would be at acute risk. Peru's agricultural and infrastructure systems face potential flooding, exceeding even the 1997 Charter 98 disaster. This reading is worth holding in your back pocket. The subsurface data supports it as a live possibility. Reading 3. The alarmist framing. That this is a tipping point that will render vast regions uninhabitable, cause permanent regime shifts in global climate, or represent the planet moving into a new stable state, does not survive the evidence. El Niño is a transient event. Every prior super El Niño ended. The system oscillated back through ENSO neutral and eventually into La Niña conditions. The 1997-98 event was followed by a sharp La Niña in 1998-99. The 2015-16 event was followed by La Niña conditions within 18 months. The coupling that is producing the current event will, on any reasonable timescale, relax. The impacts will be severe in specific regions and for specific durations. They will not rewrite the operating parameters of the Pacific on a permanent basis. The distinction matters because reading 3 produces paralysis and misallocated response resources, while readings 1 and 2 produce rational preparedness. The centered reading is reading 2 held inside the probability range of reading 1. Plan for a strong to very strong event with significant regional impacts. Watch the subsurface anomaly through August. If it maintains +6 degrees Celsius or greater as it continues surfacing in the Eastern Pacific, the upper end of the ensemble becomes the planning scenario, not the tail risk. Tonight we looked at an event that is, in one sense, perfectly ordinary. El Niño has been doing this, cycling between cold and warm phases, reorganizing the atmosphere, redistributing heat from west to east across the biggest ocean on the planet, for hundreds of thousands of years at minimum. Coral proxy records from the tropical Pacific, analyzed by researchers including Kim Cobb at Brown University, extend the ENSO record back roughly 7,000 years. The system has been oscillating, building, crashing, recovering, for longer than human civilization has existed to observe it. What is not ordinary about 2026 is the baseline. Every one of those oscillations happened against the backdrop of an ocean at a temperature determined by the natural radiative balance of the planet. The ocean running underneath this El Niño is warmer than it has been at any point in the Holocene. The roughly 11,700-year period of relatively stable climate within which agriculture, cities, and most of what we call civilization developed. When a system that was calibrated by evolution and geology over millennia oscillates atop a shifted foundation, the oscillation follows the same physics, but the absolute outcomes are different. The waves are the same shape, they are landing higher up the beach. The 12-month period from April 2025 through March 2026 was, according to NOAA and Carbon Brief's analysis, the warmest such period in the global temperature record. That was measured before the El Niño fully engaged. When ENSO adds its 0.1 to 0.2 degrees Celsius signal to a record warm baseline, the resulting absolute temperatures during peak months are entering territory the climate system has not experienced in modern human history. The instruments will keep watching. The buoys will keep sending their temperature readings up from 200 meters depth. The Sentinel-6 satellite will keep measuring the slight bulge in sea level height that tracks the Kelvin wave as it moves east. The ECMWF and NOAA and IRI models will be updated next month with a new observation window. And the ensemble will either narrow toward record territory or begin pulling back. We'll be watching. The planet is running a signal. We are slowly learning to read it. Stay watchful, stay prepared.